Hi, everybody. Okay. All right. One announcement. I haven't yet added to the presentation topics. Um, I'm planning on doing that soon. Um, it'll happen sometime this week. I'm trying to decide where to start, kind of with the next slate of topics. So I think I'll put some up. I'll definitely put some up sometime this week. Probably with options to start doing presentations next week on some topics in measure theory. I'm just trying to plan out some lectures. And I'm not exactly sure how fast I'll go. So I wanted to kind of get started a little bit first. Any questions? Might have at the time being. No questions. Okay. So let's get started. And I just remembered I'm going to share my screen. Okay. So if you remember from last time, we were asking, so we were thinking about the question of a measure. Can there exist a measure which is a measure mu on RD, where mu is a function from takes subsets of RD and spits out a non-negative real number. So maybe put this as a generalization of volume cubes, for example, such that mu is additive. So mu is additive. So what this means, make sure. So if I have, maybe let me write this as countably additive. So E1, En, possibly infinite collection of subsets. And they're disjoint. Then the measure of their union is equal to the sum of the measures of the ENs. 2, if I have two sets, E congruent to F, both of these are subsets of RD, then the measure, so meaning, say, if I just take a set and translate it or rotate it, things like this. And then 3, the measure of, so I want the measure to generalize the notion of volume. So I want the measure of the unit cube, say, is a closed unit cube. I want this to be 1. And then last time we saw there's no such measure. We showed that if we had such a measure, then we could, even on the real line, then we can quickly lead to some type of internal contradiction of these three. These three properties are in contradiction with each other. Such measures so if we restrict, if we want our measure to be such an object, where it measures all subsets of RD. And then at the end of class, we were discussing a bit. So could we, and I just wanted to emphasize, so you might say that maybe we had this axiom of choice problem or issue. And one might ask, like, can I even, well, okay. And then we also said, okay, we'd like this countable additivity thing to hold because at the end we'll be interested in taking limits of things, limiting scenarios where we want to do calculus. So we need to, we want our to know about or behave well with when there's with the infinite. But I claim that these three properties are even bad if I restrict this to finite unions as well. So there's a famous paradox, I guess. So the issue, so serious. Maybe I'll write this issue is serious. Even for finite additivity. If dimension is bigger than or equal to 3. If we're thinking of three-dimensional higher measures. And there's something what's called the Banach-Tarski paradox. Which is as follows: if I take U and V to be arbitrary, bounded open sets in RD. So any two bounded open sets in RD for D bigger than or equal to 3. So in particular, when D equals 3, which is the dimension in which we live, maybe seems to be the case. Then there exists a natural number K and subsets E1 through EK and F1 through Fk of Rd, such that the EJs are disjoint. So in particular, these are finite collection of subsets, and the union of the EJs is equal to U, the set U. The FJs are disjoint. And the union of the FJs gives V. And the EJs are congruent to the FJs. Which means they can be obtained by just by some rigid motion. So you can just rotate the EJs or translate the EJs to obtain the FJs. Okay, and this is insane because what it's saying, so the measure should be sort of preserved for the, right, if under our property 3, these are congruent to each other, so the EJs and FJs, you should think of them as having the same measure, they're the same number of them. But the sets that I started off with, U and V, are arbitrary, are two arbitrary open sets. So this is nuts. For example, I could take U to be the unit ball of size epsilon, or a size, I don't know, 1 centimeter, like a pea. This is a typical example that's given, like a pea that you eat, and I could take V to be a ball of size, I don't know what's the radius of the sun, and I could chop up a pea and the sun into equal number of pieces, and just chop them up like into the EJs. It's the same number of equal pieces, and then they have the same measure somehow, right? Like it's somehow like under if our measure was finitely additive, right? The measure of U would be equal to the sum of the measure of the EJs. The sum measure of V would be the sum of the measure of the FJs, and so U and V would have to have the same measure, right? So yeah, so this is like the obvious paradox. Yeah. So under our hypothesis, even under finite additivity, there's nothing infinite about this construction, or about the statement of this Banach-Tarski paradox. We're led to a sort of nonsensical result. Okay, so that's just mean to say that it isn't even, the problem is like worse than the infiniteness of this additivity property. You even run into problems if you have finite additivity, if you just want your measure to be finitely additive. So as we suggested the last time, what the fix to these paradoxes is nothing, is nothing really. We're going to have to just declare some subsets to be measurable. All right. So in particular, in this construction, these subsets E and F. So it's not. I'm not going to do this construction. It's quite tricky, in fact, to do this, as you might imagine. Not so tricky, but like fairly tricky to do this. I can't think of how to do it off the top of my head. Not that that's a measure of trickiness, because basically I can think of how to do nothing off the top of my head. But these subsets will end up having to be not measurable. We're going to have to kind of not allow these in our discussion of what we can measure and what we can't measure. Okay, so that's the Banach-Tarski paradox. Let's now drop the paradoxes. Know that we're not going to at the end be able to measure all subsets of RD or construct a measure that. But let's rather now build a measure that's enough. That'll be enough for the notion of a measure. That'll be enough for all of our purposes. So let's go back to rectangles and cubes. Okay. So, just a quick definition. A union of rectangles is called almost disjoint. If the interiors of the rectangles are disjoint. So you should think of two rectangles like this that share a boundary. So they share this boundary here. But then we call these two rectangles almost disjoint because they just agree on a line like this. Okay, and then we're gonna try to understand. Our first goal is trying to understand the structure of open sets in RD. But our very first step is to understand the structure of rectangles. So if a rectangle, lemma 1, So if a rectangle R is an almost disjoint union of finitely many rectangles, Rj. So R is equal to the union of j equals 1 to n, say, of Rj. Then the volume of the original rectangle R is just equal to the sum from k equals 1 to n of the, or j rather, I was calling it j before, of the sums of the rectangles that make it up. So this is this is an almost obvious lemma, right? It should seem trivial. I'm not making any statement, and the proof is just a picture, basically. So here's my initial rectangle R, and I claim this merits just a second of argument. I'll just try and illustrate what I mean by a picture. Let's say it looks like this. So remember how the way we measure the volume of a rectangle is just by multiplying the side lengths of multiplying the side length by each other. The volume of this rectangle R is just this side times this. But the ones in the interior are, on this side I only it's not a clean breakup, right? I can't. It's not immediately clear that the statement's not immediately clear with such a picture, I guess. To make it clear, what you can do is just, I have different colors. I always forget colored chalk to this lecture, and then I'm stuck, but now I have an iPad. What you do to fix it is just extend, use the outlines of the rectangles to extend, to make a grid. And now the volume, now it's clear, right? Under this bigger, so I made a bigger collection of rectangles. I subdivided my original ones a bit. Right now I have a new collection of rectangles, but now it's clear that the bigger rectangle is equal to the volumes of the sum of the volumes of the smaller rectangles, because the side lengths are just made up of the side lengths of the smaller rectangles, right? And then the way to go back is to say, well, all I did to the smaller rectangles was divide them up into two rectangles in the same way, and so the proof is complete. Okay, so this is kind of an obvious lemma. Okay, I'm not going to dwell too much on this. Just think about it a bit. If that wasn't clear, or if the picture I drew wasn't clear. Okay, lemma 2. Lemma 2. If R, R1 through Rn are rectangles, this is almost the same lemma, are rectangles, and R is covered by the union of the Rj for j equals 1 to n, then the volume of R is less than or equal to the sums of the volumes of the RKs. All right, and then the proof is the same, but without almost disjointness. there may be overlap. Okay, and then this leads to, that's what leads to less than or equal to. The fact that it's this same picture, but maybe some of the rectangles overlap with each other. So I only get this upper bound for the volume of R. Okay, so with these two very simple lemmas, we can understand the structure of open sets in RD, or we can give some understanding of the structure of open sets. So the theorem, part one of the theorem is this is the structure of open sets in the real line. In R, so every open set O in R can be written uniquely as a countable union of disjoint rectangles or disjoint intervals. Countable union of disjoint open intervals. So this is a powerful theorem, right? It's telling you no matter how crazy how crazy the set is, if it's an open set in the real line, then it's just a countable. All open sets in real line are just a countable union of disjoint open intervals, and it's uniquely expressible as such. Two is the structure of open sets in RD. For d bigger than or equal to 1, in particular for d equals 1 as well. So we don't have such a strong theorem in RD. The direct analog would be you could express every open set in RD as a countable union of open rectangles. It's not true, and even for d equals 2, as you'll see in your homework. So one of the homework problems is to find a counterexample to this statement and for d equals 2. But we can weaken the statement slightly, and it'll be enough for our purposes. So every open set in RD, every open set, call this O in RD, can be written as a countable union of almost disjoint cubes. Sorry, closed cubes. Almost disjoint closed cubes. Okay, so we're losing two things in 2. We're losing the being able to use open sets to do this, to express as a countable, and 2, maintaining the uniqueness of this expression as a countable union of cubes. So there are possibly many different ways of finding these cubes. Okay. Any question about the statement of the theorem? If not, I'll show the proof. Okay, let's prove 1. So let's take an open set in the real line. For every x in O, let I sub x be the largest be the largest interval, open interval, um, containing x, such that Ix is inside of O. And how do I make such an Ix? So just let A sub x to be equal to the inf over all A. We're going to use the least upper bound property. The inf over all A less than x such that AX is an O and BX is the soup over all B bigger than X such that XB is an O. And this note that this implies that AX is less than BX. O is an open set, so there is at least some interval that contains X inside of the open set. So AX is strictly less than BX, and just let IX to be equal to the interval AX BX. And then Ix is inside of O. This property is satisfied because of the definitions. And then therefore, since I've done this around every, so O is equal to the union over all X and O of the IXs. Right, since I did this around, I could do this around every X in the set O, so O is equal to this union. Each of these sets is inside, so I can take a union of them. Now suppose, okay, but then I'm not done, right? Because I claimed I can do this with countably many open sets, right? So I'm going to try to understand something about these sets IX. Now suppose that IX intersect IY is not empty. So suppose I have two different points, X and Y in O, and I look at IX and IY, and these are not empty. This means that IX union IY is in O, and X is in both, and there exists an X, or maybe just X, sorry, X is I've already called it X in IX union IY. But since IX is the maximal such interval, this is a union of two intervals, so I get another interval. It's maximal and containing X. This means that IX union IY is inside IX and inside IY, which implies that IX is equal to IY. Therefore, any two distinct intervals are disjoint. So I've not only expressed O as a union of intervals, I've now claimed that I've expressed it as a disjoint union of intervals. These are all distinct. Now we just use the density of the rational numbers. So note every IX, remember this is an open interval, contains a rational. And just enumerate using the rationals. This is my set O. Is a union of IX. Is a countable union. Okay. All right. Did this make sense? This proof, though, I just looked at every point in the set, took the maximal open interval containing that point, and then as long as I don't double count, I have a disjoint union, and now I just want to label each of these intervals, label each of the distinct intervals, and each one has a rational in it. And so I can label them with, and those rational numbers are distinct, right? Each rational number can't be in two different sets because no element can be in two of these different sets, as they're disjoint. And so now just my labeling by rational numbers tells me that this is a most countable union is a at most countable union. Okay, so so now I claim that this this looks like it. I'm now just able to define a measure on open sets of the real line, right? Because I can express each open set uniquely as a disjoint union of open intervals. I know how to measure the length of each interval. And so I should just declare the measure of such sets to be the sum of the measures of all of these intervals, possibly infinite, right? So if O is open, and O is equal to a union from, sorry, J equals 1 to infinity of open sets ij for some countable union. IJs are disjoint. A natural candidate for the measure of O is just summing the lengths of all these intervals. But okay, there are just the main issue is, I think, is that this is so the issue with this definition is I just proved a very strong structure theorem for open sets, and the structure theorem doesn't carry over to to other sets, so it's hard to generalize this. To sets that are not necessarily open. Okay, so let me prove the second component. So the other reason why this is insufficient, kind of as a definition of measure of measure, just is not just it's hard to generalize so the sets are not open, but it's also hard to generalize to RD, namely because we could we have this, we're going to prove this structure theorem, but and then a natural candidate for a measure of an open set in RD would be just taking the sums of the measures of these disjoint union of rectangles or of closed cubes. Just almost disjoint closed cubes. But then since I don't have a uniqueness statement here about this decomposition into cubes, I on the one hand wouldn't know if my definition was depends on how I decided to chop the open set into cubes. So let me just prove too about the structure theorem, but to say that at the moment we don't really have a good definition of measure yet. A generous letter. Mostly the proof of two. So proof of two. This is actually, or maybe we'll start on this next page. This is actually not so hard. So I have some open set. So I'm going to try and express this open set as a countable union of almost disjoint rectangles, or cubes rather. And the way I'll do that is I'm just going to I'm going to superimpose on this a grid, finer and finer grids. So let's start with a grid like this. This is supposed to be an even grid of RD. And it's going to be a stopping time argument. So the first grid length, so subdivide into grid of side length 2 to the minus n. So I'll make this first this unit I'll make this first pass unit cubes, and then I'll declare a cube good. So 1, declare a cube good, a cube q good if q is inside of O. That are I accept this cube into my decomposition. 2, cube q is bad, and I discard it if q intersect O is empty. So maybe this is a good cubes will be blue, maybe. Did I make any good cubes? No. So no good cubes yet. This, let's make the red cubes bad. This cube is bad. It doesn't intersect with the set, so I throw it out. This cube's bad. I throw away the cubes that are bad. And then 3, the cubes that are neither good or bad. All other cubes are temporarily kept for my decomposition. So I just I don't call them good or bad yet. But what I do to the cubes that I keep is I divide those up. So I just divide those into into 4, in this case 4 for d equals to 4 new things, 4 new cubes. And now I re-examine. So I throw away all the bad cubes, the ones that don't intersect with my set at all. And some good cubes I'm going to keep. So I keep, this is good, this is good, this is good, etc. And then I temporarily keep the ones that are neither good nor bad, subdivide those into, again, I chop those into equal pieces again, and then I keep going like this. So this process, so iterate this process forever. And at each step, I'm only producing I'm taking a step each time. At each step, I'm only producing countably many acceptable cubes, right, that I keep. So I at the end I obtain a countable collection. Um, so so this is the proof. Iterate just forever, and at the end I produce a countable collection. And the only ones that I end up keeping, I don't keep on subdividing, are the ones that are fully inside the set. Um, so and note that so did I get everything? Note for every x in O, there exists a cube Qn such that Qn has side length 2 to the minus n, and Qn, sorry, Qn inside O. So it's an open set, right? So so if I have this open set, if I have any point x in it, eventually there's a cube in this decomposition that has small enough side length that's totally inside, right? Okay, so that's the proof. And again, as I said out loud, the seemingly natural definition of measure of such open sets would be the measure of O is equal to the measures of I'll call these rect QJ. This countable collection of cubes that I built in the previous step, but it's not clear if this measure is independent of choice of the QJ. So there's no, I gave you one construction of this decomposition of the set into disjoint cubes, and right there, this construction is not unique, or I didn't prove that it was unique. So it's not clear that such a measure would be independent of the choice of cubes. So we're not ready yet to define a measure. But we do now know about the structure of open sets, which is a good first step. Okay, but let's move on to the delicate question of size of a set. And we'll kind of illustrate this in the context of an example, which is a source of it's a very nice example and a source of a lot of interesting other examples, and just it's helpful when thinking about things. One tricky thing in this business is to try and figure out what's easy and what's not easy, and this example will help us not get too easily fooled. Maybe is a good way of putting it. Having such an example in mind. So the example is called the Cantor middle third set. And it's constructed as follows. So I take C0 to be equal to, so C for Cantor, and the interval 0, 1. C1 to be the union of two intervals, interval 0 to 1/3, union the interval from 2/3 to 1. C2 to be equal to the interval, maybe I'll start drawing the picture now. C2 is 0, here's 1. I keep the interval 0 to 1/9. I keep the interval 2/9 to 1/3. I've thrown away at the previous step the interval from 1/3 to 2/3. I keep 2/3 to 7/9, and I keep 8/9 to 1. Sorry, these should look like equal sets. So there are 4 sets in C2. There's one set here, 2 to the 0 sets here, 2 to the 1 sets here. This is equal to 2 to the 2 sets here. A union of 2 to the 2 sets there. And I go on like this. So at each stage, I just take the middle third of each interval that's left and erase it. Okay? So I just take the open middle third of each thing left. So that to get from step 1 to step 2, I just erase the middle third of this interval and the middle third of this interval. And so I keep going like this forever. And I yield a sequence of compact sets. So this process compact sets that's nested. Oops. Goes on forever, and I let C is equal to the infinite intersection of the CK, of the set CK. So I take the intersection of all these sets. And let's think about what we have left. What's left. So note, so let's make some observations. This is not the empty set. For example, because 0 stayed in at each stage. I'm always erasing the middle thirds of the remaining intervals, so 0 stays forever. 1/9 stays forever too. All of the, in particular, all the endpoints of these intervals are in the set. So 0, 1/3, 1/9, etc., 1/27, these are all in the set. This is not equal to 0 since all endpoints of CK are in C for every K. So there's lots of stuff in the set. Or some other observations. It's an intersection of closed sets. Right? So there's closed sets, so it's closed. Closed and bound, and it's bounded. Right, because it sits inside the interval 0 to 1. And these two, because we're sitting inside of the real line, means it's compact. The compact set. Some other more refined properties. One is it's totally disconnected. What's this mean? It means what you kind of imagined it might mean. It doesn't contain any intervals. So for every x, so i.e., for every x, y in the Cantor set C, there exists a z that's not in C, such that z is between x and y. So it has no intervals at the end. And then C is what's called a perfect set. C is perfect. So it seems like a judgment, which is it's a technical word. It means I always have to look up what this word means. It's closed and has no isolated points. So there's no points that are just isolated from every other point. Okay, so now we ask, how big is C? So how big is this set? In the context of the question that we're talking about with measure. So how big is C? What's its size? So what should its measure be? And now this really depends on how we're thinking about it. So on the one hand, in real analysis, we thought a lot about the size of sets using notions of like, are they a countable collection of sets or an uncountable set? Well, it turns out that C is, we can think about its cardinality. And is uncountable. So you could, in fact, has the same cardinality as the real numbers. So it's not a countable set. However, we think of its length as being, so there are a lot of points in the Cantor set. In fact, there's an uncountable number of points in the Cantor set. However, it's very natural to think of it as having zero length. However, we think of it having zero length. Why? Well, it's covered. The resulting set is covered by each of the sets. It's built as an intersection of these sets. So any one of these sets, and these are nested. So any one of these sets CK, which is a finite collection, each CK is a finite union of intervals, covers the whole set, right? Because we obtain each next step by just erasing points from the previous one, erasing a third of each of the previous sets of the previous set. So note C is covered by CK for every K. And how big is this? How big is each set CK? Well, it turns out they end up getting very small, right? I mean, you can see this in the picture. The length of each of these sets is decreasing. It gets smaller and smaller. So the length of the CK goes to 0 as K goes to infinity. Why? CK is a disjoint union of 2 to the K intervals, each of length 3 to the minus K, right? The length of the first one is 1. The length of the second one is, of each of these second intervals, is a third. So 3 to the minus 1. The length of each of these other ones is a ninth. So 3 to the minus 2. The length of the next collection of intervals is a 27th, 3 cubed. So the length of CK is equal to 2 to the K times 3 to the minus K, which is 2/3 to the K, right, which goes to 0 as K goes to infinity. So since the Cantor set sits inside each of these CKs, there's kind of no good measure of length that generalizes the length of an interval for which the Cantor set doesn't have measure 0. Okay, so only of measure of C. Okay, so this at the moment, so this is a nice construction. We'll keep this example in mind as we go throughout. But at the moment, we've just illustrated the point that notion of size given by cardinality of a set, even if we're just thinking about the real line, is distinct from our notion of length.
Professor?
Yeah.
Is it also possible that we could say C is unmeasurable? Is that a possibility?
Yeah. So we haven't decided which sets are measurable yet, right? I guess what I just wanted to say at the moment. So later on, we'll see that the Cantor set will be a measurable set, and will be a Lebesgue measurable set, and it'll have measure 0. I just want to illustrate that if we think of at the moment as we're thinking of just generalizing length, this set should have measure 0 since it sits in it's a subset of arbitrarily small sized sets, where we're just generalizing the notion of the sets where we should measure the length of, right? We think we can measure the length of each of these sets ck because it's just a finite collection of intervals. So we should be able to just disjoint intervals, so we add their length together. Yeah, so but you're right. At the moment, we haven't decided which sets are measurable or not. Okay. All right. So let's get to building the Lebesgue measure. And it's going to be built from what's called an exterior measure. So an exterior measure. This is not measurable yet. We're gonna define what's called the exterior measure of a set. So definition: let's let E be a subset of RD, be any subset. Then the exterior measure of E is given by mu lower star of E. So this is our notation for exterior measure is going to be mu lower star. Is defined by the inf over all sums j equals 1 to infinity, qj, where I need to tell you which sets are, which of these are allowable under the inf. So where inf is taken over all countable coverings, by closed cubes. So I obtained the exterior measure of a set by covering it by some arbitrary collection of closed cubes. I just need I'm just allowed to use cubes to cover it, but I take any collection of closed cubes I want. Sum up all the lengths, all the volumes of those cubes. I know how to compute the volume of a cube, right? It's the one thing I'm starting off by knowing. And then I take inf over all these possibilities. So if I have a set like this, I can just take some cubes that cover it, sum up the volumes of these cubes that I covered my set with, and then but then now I have to take inf over all such possibilities. They can inf over all such possibilities. Just a remark is that, well, this is non-negative, but it's possibly infinite, right? I'm allowing for the possibility this is infinite. So it's possibly infinite. Which is good, right? Because I'm allowing for in my definition, I can measure all subsets of RD. In particular, I can measure the size of RD itself, which will be infinite. Okay, so one comment is that the choice of using one remark is that I've decided to use cubes to construct the exterior measure. I could have also chosen to use open balls or rectangles, and we'll end up getting the same thing. It turns out we're going to end up in the same place. But I need to allow these infinite sums. It turns out that if I want to take finite coverings of cubes, this wouldn't quite be good enough of a definition. Okay, so some examples. Let's try to measure, let's try to compute the exterior measure of sets. some examples. We're gonna do a bunch of these. It's not so easy. One, the exterior measure of just a set given by a single point x is 0. Okay, that one I claim is okay because I can cover x by an arbitrarily small cubes of arbitrarily small size, say centered at x, right? And so so I just take inf and no choice but this to be 0. So that example is an easy one. Second example, the exterior measure of a cube, of a closed cube, is equal to the volume of the closed cube. If Q is equal to a closed cube. So I'd hope this to be true, and it is, but I claim that this one needs a little bit of argument. So proof of 2. So I'll give an argument. It's a good example of how to argue some of the argue in this vein. So one, Q covers itself. So so the mu star of Q is less than or equal to the volume of Q. Right, because the exterior measure is given by taking an inf, and here's Q is just covering it by itself with one set as an example of a covering. Sorry, Faraz, is your hand there? Oh, okay. I can lower it. Okay, that was from the previous question. Gotcha. Okay. Q covers itself, so its exterior measure is less than or equal to its volume. But on the other hand, now consider an arbitrary. So I want to prove the opposite inequality. That consider now an arbitrary covering. Q is inside the sum from j equals 1 to infinity of qj. It suffices to show that the volume of Q is less than or equal to the sum of the volumes of the qj, right? Because I'm taking inf over all such coverings, and as long as this measure, the volume of Q is less than this, then I'm good, right? So for every qj, find an open cube Sj such that I claim I can find such a cube. Qj sits inside of Sj, and Sj, the volume of Sj is less than or equal to 1 plus epsilon times the volume of Qj. So I have a closed cube, and I just find, I don't know why I needed to make both of these so small. So this is the Sj, and this is Qj. So Qj is a closed cube, but now just slightly enlarge each of these in such a way that I don't make the volume of Sj bigger than 1 plus epsilon times the volume of Qj. Where epsilon is a number that is arbitrary. So just you give me an epsilon, and I find the Sj's accordingly after you've picked an epsilon for me. So Sj's. So then the union of the Qj's covered Q. So the union of the Sj's also cover Q, since I've just enlarged each of the Qj's. So in particular, this is an open cover. It's an open covering of Q. And Q is compact implies there exists a finite subcovering. So there's a finite collection as j equals 1 to n, such that Q is inside the union from j equals 1 to n of the SJs. So I can refine my possibly infinite covering to a finite one. Now take the closures of each SJ. These are now closed cubes, right? And by the lemma we prove, I think I call this lemma 2. By lemma 2, the measure of Q is less than or equal to the sum from j equals 1 to n of the measures of the SJs. The SJs are possibly overlapping, right? But remember, if I take a cube and then cover it by other cubes, then other finite collection of cubes, then the volume of Q is less than or equal to the sums of the volumes of the SJs is finite sum. But now the volume of Q is less than or equal to each of these is less. Each of the volumes of the SJs is less than or equal to 1 plus epsilon, right? This is less than or equal to 1 plus epsilon times the volume from j equals 1 to n of the corresponding QJs, which is less than or equal to 1 plus epsilon, the sum from j equals 1 to infinity of the QJs. Adding now in the rest of the QJs that I threw out after refining to my finite subcover. So here I use this easy lemma that I stated at the beginning of class, lemma 2, as the crux in the proof. And we're done. This is enough. Arbitrary. Okay, did that make sense? Does anyone have any questions, rather? Frost?
When does it matter when we have open cubes or closed cubes?
So when does it matter?
Yeah, like maybe I forgot to write this down, but did lemma 2 involve only open cubes or only closed cubes, or?
Okay. So lemma 2 was just about closed rectangles, or lemma 2, where are we? So these are closed rectangles in lemma 2. But the I think what's funny here in this proof is that we like pass to open rectangles and then pass back to closed ones and stuff like that, right? I think this is what you're asking about. So the crucial step here was kind of this refining. So the important component of lemma 2 is that it was for finite collections of a finite collection of rectangles, not that they were closed or open, but that the statement was true for finitely many rectangles. And here in order to obtain finitely many rectangles, we wanted to use the fact that the set we were trying to define the exterior measure of was compact, and then we found we took an arbitrary covering of closed rectangles, enlarged those slightly to get a covering of open rectangles, use compactness then to refine to a finite subcollection, and then use lemma 2 to estimate the measure of the volume of that finite subcollection. Estimate the size of the initial set by the covering, finite covering of that set. So lemma 2 is more about the finiteness, kind of. Okay. Any other questions? Okay. All right, a few more examples. So example three, um, if I take uh, Q and an open cube now, um, then then mu star of Q is equal to the volume of Q. Um, this is true since the volume of Q closure is equal to the volume of Q, which implies that mu star Q is less than or equal to the volume, right? Because its closure is a covering. And then if um, if Q0 is closed and Q0 is inside of Q, then Q0, then we proved this already for Q0, and we know since it's inside, it's less than or equal to mu star of Q. And then therefore, uh, um, since the volume of this closed cube is the volume of any closed cube sitting inside is less than or equal to the measure of the exterior Q, we can choose such a closed cube kind of arbitrarily close to the measure to the open cube. Can choose as close as we like, and this will lead to the volume of Q less than or equal to this, the opposite inequality. Okay, and then the last example, R is a rectangle. Then mu star of R is equal to the volume of R. And so same argument as before for cubes implies that the volume of R is less than or equal to the exterior measure of R. It's the same argument as the same inequality we proved for closed cubes. For the reverse, make lattice or grid in RD of size 1 over k. So make lattices in RD of size 1 over k. So divide RD up like this, where the length here is 1 over k into cubes. Let script EQ be equal to all cubes in lattice such that Q is inside R, and Q prime is all cubes such that Q intersect R is not empty. And Q intersect R complement is not empty. And this implies that R is a subset of all of the, so we just keep all the lattice squares that overlap with the set that we overlap with R. So it's inside here. It's all Q inside of Q union Q prime. Q. And it's not so hard to show that if you just take the cubes which are all the way inside, then you get something that's less than or equal to the volume of R. Um, um, in script Q prime, there are this is a little bit trickier. There's big O of k to the d minus 1 cubes, since the boundary of R, since to be in the here's R, the ones in Q prime sort of overlap with the boundary, right? The boundary is d minus 1 dimensional, since the boundary of R is d minus 1. And the volume of each is of size k to the minus d. So I have k to the d minus 1 many of cubes of volume k to the minus d, which means that the sums of the volumes of the qj's, where q is in script q prime, is equal to O of k to the minus 1, which means that the sum for all q and script q prime qj is less than or equal to the volume of R plus a constant times 1 over k, which now implies that that exterior measure of R is less than or equal to the volume of R, but just by letting k go to infinity. Okay. All right, and I think I'll stop here for today, and we'll pick up fleshing out exterior measure next time with a couple more examples, actually. Any questions before we go? Yeah.
For the closed cube case, when we did the expansion, why couldn't we use the same strategy that we use with the open cube, which is just start with the cube inside and just inflate it until to prove the lower bound?
It back here, right?
Yeah.
Back here.
Yeah.
Okay. So we need to start. We're using in the second example you're talking about. We're using the first example.
I see.
So we needed the first example. We need to consider all arbitrary coverings.
Oh, I see. Okay.
In the second one, we're kind of applying the hammer we obtained from working at the first example.
Okay, got it. Thank you.
Okay, everyone. There are no questions. I'll see everyone on Thursday.
Thank you.
Bye, guys.
Thank you.